Please read the notes very critically. Don't believe anything I say. Okay? Any questions on the logistics? I have office hours today from 10 to 11. And I have office hours tomorrow from 11 to 12. And I posted one practice midterm exam. I will do another practice midterm exam on Tuesday. And on Monday also I have office hours from 10 to 11. So please come see me. Let's look at a movie here. Oh no. Okay, watch the movie here. Let me play that over again. Oh. What does it do that? Go back to. So, what do you think I'm showing here? A reaction, exactly. Erica, I didn't understand you. Did you say something, Erica?
Pardon?
Did you say something?
No, I just sneezed.
Oh. See, I try my best to answer every. What you're seeing is what I would call a nanoscopic view of how a chemical reaction occurs. We're looking at a chemical reaction at the atomic level at a time scale of femtoseconds. What is a femtosecond? What is a femtosecond?
1,000?
Tamara?
Maybe 1,000? No.
10 to the negative 6?
12, 10, 20.
10 to the negative 15
Wow.
femtoseconds. We have tools now that can observe chemical reactions on the scale of femtoseconds. This is what is called reaction dynamics, which is a part of chemical kinetics, and that's going to be the topic of today's lecture. Chemical kinetics is the study of how fast a chemical reaction occurs. We're going to look at the difference between kinetics and thermodynamics. Remember, we spent the last 6 lectures looking at thermodynamics. We will see how to define a reaction rate. We will talk about what are called rate equations, which can either be differentiated rate laws or integrated rate laws. So this is an example of a differentiated rate law. This is an example of an integrated rate law. You go from a differentiated rate law to an integrated rate law. A differentiated rate law tells you how the rate depends on concentration. The integrated rate law tells you how the concentration depends on time. And we will look at different types of reactions. We will talk about zero order reactions, first order reactions, and second order reactions. And then we will talk about experimental methods to determine rate laws. And we will talk about 4 methods that are used to study rate laws. So that's the big picture for what we're going to do today. So, how would I fill in the blanks here? Yes, Tiffany?
How fast a reaction occurs.
The study of how fast a reaction occurs is called chemical kinetics. Very good. What is this here? It's the exhaust system in an automobile. I don't know, I think maybe a few years ago, people were stealing this component here from cars. This component is called the catalytic converter, and catalytic converters contain quite a bit of platinum. It's a very expensive metal. What the catalytic converter does is to convert noxious gases such as carbon monoxide and nitric oxide into less noxious gases such as carbon dioxide, N2, and water. Okay? The catalytic converter speeds up the conversion of this to this. So a catalyst is a very important part of chemical kinetics. Because thermodynamics might tell you that a reaction is favorable, but if the reaction is very slow, then it's not a very useful reaction. We need to speed up chemical reactions quite often. And this is a case where catalytic converters play a very, very important role in safeguarding our environment. So in chemistry, we wish to answer two central questions when we look at chemical reactions. What are the two central questions? What is the first question? You can take a hint, look at this.
Which law of thermodynamics do we use in a chemical reaction? Or we have to use that to explain.
Okay, the laws of thermodynamics help us answer the first question. What is the first question? Neha.
Is a reaction favorable?
Exactly. Is the reaction thermodynamically favorable? The second question is how fast the reaction will go. These are the two critical questions that we need to ask. The difference between thermodynamics and chemical kinetics is best illustrated in this diagram here. Can you take a couple of minutes, a minute to quickly talk to your neighbor and figure out how best to distinguish between thermodynamics and kinetics based on this diagram, please? So talk to your neighbor for a second or a minute. Alda?
So like,
Maria now. Okay.
so the reaction is favorable.
So what I was thinking is
And that has potentially you know that so like the higher thermodynamics still change direction of the reaction.
I think that can answer the question, how is it to avoid the reaction?
So what determines the thermodynamics of the process? The potential energy, the potential energy difference between the reactants and products. So this here, if you may want to think of it, you can think of this as delta G. Okay? And so that's thermodynamics. Kinetics is determined by Tamara?
The activation energy. So it's that the space between the reactants and that top transition.
Right,
So that-
the energy between the transition state and the reactants is the activation energy that determines the rate of a reaction. We looked at the difference between thermodynamics and kinetics, and we said that the diamond is so I want you to fill in the blanks with thermodynamically or kinetically. A diamond, yes, Angela?
A diamond is kinetically stable.
The diamond is kinetically stable, correct? And why is that, Angela?
Because graphite is a more stable form than diamond, but graphite doesn't go spontaneously to diamond.
Graphite does go spontaneously to.
The process is really slow.
It is slow. Has a very high activation energy. Therefore, we say that diamond is kinetically stable and graphite is thermodynamically stable.
Wait, so graphite can go from back to diamond?
Graphite will turn to diamond given sufficient time.
Okay.
Diamond will turn to graphite
Yeah.
given sufficient time. Graphite is more thermodynamically stable than diamond. Okay. Did I say it wrong first? No.
You said, I think someone said it was graphite turning into diamond.
No, diamond turning into graphite is favorable thermodynamically.
Diamond to graphite is kind
Exactly.
Which is why diamond is kinetically stable.
No, that's different. Okay? Diamond is here and graphite is here. Okay? If the reaction was like this, then you wouldn't say that the diamond was kinetically stable. But because the reaction is like this, we say that diamond is kinetically stable.
Why does the height difference make it kinetic?
Because it's much,
Okay, go ahead, Tamara.
I feel like it's much harder to actually cause it to change because a lot of the activation energy is really high, so it's less likely to happen.
We're going to see very shortly that the rate constant is going to be equal to A times e to the power minus e sub A over RT. The higher the activation energy, the lower the rate constant. We're going to look at this in more detail on Monday. Okay? So the higher the activation energy, the slower the reaction. Okay?
So you can say that diamond to graphite is thermodynamically favorable.
Uh-huh.
Therefore, it's thermodynamic. Therefore, graphite is thermodynamically stable.
Right.
And then graphite to diamond would take sufficient time and energy.
Diamond to graphite conversion can take place, but it takes a very long time because the activation energy is very large.
Oh, that's not diamond to graphite?
This is diamond to graphite.
Wait, how about graphite to diamond?
I mean, that's not thermodynamically favorable.
Okay, so that's...
I mean, but you can change the conditions to convert graphite into diamond. But under normal conditions, that's not a spontaneous process. Okay? It doesn't mean that it won't happen at all. But if you have equilibrium, at equilibrium, graphite is going to be favored compared to diamond. Okay? So let's look at what we mean by a rate of a chemical reaction.
Pouring bleach into a beaker of water and blue food dye converts the dye molecules into a colorless form. The timer indicates the progression of the reaction. If we plot the concentration of dye molecules at various times over the course of the reaction, we can determine the rate of the reaction.
Okay, so if you measure the concentration of the reactants or the products as a function of time, we can figure out the rate. Okay? So here is a diagram that is plotting concentration as a function of time. And we're going to define the rate of a reaction in one of three different ways. If we want to know what is the average rate of the reaction between this time here and this time here, we look at this height, we look at this distance, rise over run gives you the average reaction rate. And that's the average between time t equals 50 and time t equals 150. Quite often, we are not interested in average reaction rates, we're interested in instantaneous reaction rates. So if we are interested in the instantaneous reaction rate at time t equals 150, we take this curve here, and what do? Draw a tangent, and that slope of that tangent gives you the instantaneous reaction rate. What do you think initial rates are?
The very beginning.
Can somebody define it for me?
The derivative of the curve at time 0.
The derivative of the curve at time 0. You use the word derivative. Okay. I'm not going to expect you to know calculus, but if you know calculus, the treatment is a lot more elegant and beautiful. If you don't know calculus, it's not going to hinder you. Wherever I say d a dt, this is calculus. If you don't know calculus, we're going to say this is delta A over delta T. Okay? A is the substance. In square brackets is the concentration. So it's the change in the concentration over the change in time. Change in the concentration is here. Change in time is here. Questions? Angela, you had a question. Okay, so things get a little bit more interesting than what we talked about. So let's look at this reaction here. If I use N2O5 as the substance of choice in writing the rate of the reaction, and if someone else uses NO2 as the substance of choice when writing the rate of a reaction, our values are going to be different. Because N2O5, the rate of disappearance of N2O5 is going to be half the rate of appearance of NO2. Does everybody understand that? The rate of disappearance of N2O5 is going to be half the rate of appearance of NO2. Yes, Rachel?
Is that just because there are half as many moles of N2O5?
It's the ratio is 2 to 4, 1 to 2. All right? So when we write the rate of a reaction, we have to be cognizant of the stoichiometric coefficients, because we don't want to have two different answers. Whether you write the rate or I write the rate, whether you choose one molecule or whether I choose another molecule, the rate should be the same. We can't have two different answers. Okay? So what we do is we say dN2O5 dt, but we're going to divide by 2 here. The 2 that's here, we're going to divide here. For NO2, we're going to divide by 4. And for O2, we're going to divide by 1. So if we divide this quantity by the stoichiometric coefficient, we ensure that everybody gets the same answer irrespective of the choice of the reactant or product in expressing the rate of the reaction. Yes, Kirsty.
Why is the 1/2 negative?
Why is the 1/2 negative? Lauren.
It's the disappearance of N2O5.
Yes, because we're talking about the disappearance of N2O5. Okay? This quantity is going to be a negative value. By putting a negative in front, we ensure that we have the same value. The rate is defined to be a positive quantity. Okay? So I have made a slight jump from this reaction to my favorite reaction here. And here is the rate for that reaction. All right, the rate of a reaction depends on 4 quantities. And I'm going to illustrate each of these quantities with a movie.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
Okay, so what's my next choice here? Can somebody tell me? Effect of concentration. No. Okay, actually, I think maybe this one here.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
Okay, usually when you increase the concentration, the rate of the reaction increases. I've been putting these movies into these folders for in your Dropbox. Is that helpful?
Yeah.
Okay, I think this is the first time I've ever done that. Are we approaching the limit of 2 gigabytes yet? We're getting close?
Well, I mean, I use my Dropbox for other things, but mine's almost.
The Dropbox is only 40.2% full.
How much is it?
40.2% full.
Oh, so because you're using other stuff, okay. So at some point I'm going to delete maybe the first 20 lectures. But all you have to do is to just copy it and put it onto your hard drive. Yeah. Just copy the folders, the first 20 folders, copy it and paste it onto your hard drive. Then you can have it permanently. And when you're 95 years old, you can still watch the movies No? All right, whenever Rachel tells me to delete, I will delete. Okay, but I will give you 24 hours warning. All right, what's the next one?
Temperature.
Temperature.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
Okay, usually when you increase the temperature, the rate constant increases, the rate increases, and that behavior is summarized in this very simple, elegant equation called the Arrhenius equation. We will talk about that soon. Anybody miss Sakai, that I'm not using Sakai? You know, there is a 450-page manual for Sakai. I was going to propose to the administration that I spend my entire sabbatical working on understanding this 450-page manual. All right. So, I have one more, right?
Presence of a catalyst.
Effect of a catalyst.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
All right. So those are the 4 factors that control the rate of a reaction. Now let's get quantitative. So the reaction that we just looked at, hydrogen peroxide, the decomposition of hydrogen peroxide, the rate of decomposition of hydrogen peroxide is proportional to the concentration of hydrogen peroxide, and the proportionality constant K is called the rate constant. This information is obtained by doing an experiment. You cannot determine this information by looking at a balanced equation. You have to do experiments to determine the rate law. This is called a differentiated rate law because you have a differentiation on the left-hand side. If you haven't taken calculus, just make this conversion from this to this. Wherever you see this, you can write this. Okay, this is an example of a differentiated rate law. This is for the decomposition of hydrogen peroxide. For my favorite equation, rate, if expressed in terms of the concentration of A, the rate is equal to K, the rate constant, times A to the power X, B to the power Y. Note the fact that X and Y are not necessarily equal to A and B respectively. This is one of the most common mistakes that students make, is to assume that X and Y are equal to A and B. They are not. They could be, but you have to find that out experimentally. K is the rate constant, and here, so whenever you're doing an experiment in kinetics, when you're trying to determine the rate law, what you're trying to determine are these 3 parameters, K, X, and Y. Those are the 3 unknowns that you're trying to determine in an experiment. So here are some examples of rate laws for different reactions. And in this column here is the temperature and the corresponding rate constant. Okay, don't make the mistake of using capital K here. This is lowercase k. What is capital K? the equilibrium constant. The lowercase k is the rate constant. We say that this differentiated rate law is a first order rate law because power to the power to 1. Okay? This x here is equal to 1. Because x is equal to 1, we say that this is a first order reaction. If you have the more general case, the overall reaction order is
X plus Y.
x plus y. Okay, so we looked at a differentiated rate law. The differentiated rate law tells you how the rate on the left-hand side depends on concentration. But when you're doing experiments in a lab, it's hard to measure the rate directly. So the differentiated rate law is not as useful. What is more useful is the integrated rate law. So this is the differentiated rate law. If you integrate this law, you get the integrated rate law, which tells you how the concentration depends on time. How you go from here to here, we'll talk about it a little bit in class, but I'm not expecting you to know or remember any of the calculus that you learnt in Math 115 and 116. But just to illustrate the usefulness of math, I will talk a little bit about how to go from a differentiated rate law to an integrated rate law. Okay? But it's not critical that you understand that. So here is an example of a zeroth order reaction. A zeroth order reaction means that the reaction is dependent on the concentration to the power 0. That means that the rate is independent of concentration. And here is an example of how that could be. Supposing you have a platinum surface and you have molecules in contact with the platinum surface, and only those molecules that are in contact with the platinum surface are undergoing a chemical reaction. Then whether you have a lot of molecules in the gas phase or whether you have few molecules in the gas phase, it doesn't matter. So we can say that the rate of the reaction is independent of the concentration, or in other words, it's dependent on the concentration to the power 0, and therefore this is the differentiated rate law for a zeroth order reaction. So minus dA dt is equal to k sub 0. 0 here refers to the fact that we're talking about a zeroth order reaction. So what would the reaction rate as a function of concentration look like? If we plotted, what would the graph look like?
Yeah, all over the pond. Would it be a positive slope? So it's just gonna go up and then it's gonna
Angela?
Just make a horizontal line.
It's going to be a horizontal line. So this is rate as a function of concentration. This is for a zeroth order reaction.